goals.
All right, so yeah, I'm Ben Wittbrodt. I'm going to be presenting on a paper that we wrote. I wrote with John Brennan and Dr. Pierce about 3D printing PV modules, so solar panels, racking for dramatically lower than how much you can buy it right now. So here's kind of an evolution of some of the RepRap 3D printers. We have the first version, the Darwin over there on the left, and then it kind of got a little less complicated, a little more streamlined with the second version of the, which is called the Mendel, and then we have kind of the new version of the Mendel, or like Proust Mendel. They're just kind of different versions, and we can see kind of how they've come from the beginning. So our goals were to, this is the current commercial racking for RVs. It may seem a little weird to be talking about RVs right now because not a lot of developed countries have a lot of RVs, but it's kind of like a proof of concept that we're working on. So this is the traditional racking where you have your standoff to lift it off the roof if needed, and then you have these Z brackets, which I've passed around some 3D printed versions of those so you can kind of see what they look at. We used our own kind of optimized Prusa, we like to call it optimized because we think it's better, to print all the parts for the racking, and you can make it a lot less expensive, and it can perform the exact same, if not better, than the commercial alternatives. So a little background on the RepRap. Everything here, we got an open RC car. All the plans are open source. You can get all the files, all the designs that you can contribute to the community if you want. We've got like a little model of a house, a couple of gearboxes here, and then another picture of one of our RepRaps. So they cost between $500 and $800, kind of depending on what you want to do with it. There's fully functional 3D printers, and they can also print about 60% of themselves if you don't take into account like the nuts and bolts. So all these blue parts and everything, those are all printed. So the cool thing is you can either repair the printer yourself, or you can print out a new printer for someone else to use. So you can kind of, if anything breaks, you can kind of be ready to go with spare parts if you want. And the project started in 2006 in the UK, and it has absolutely exploded ever since up until now. Where there's many different designs, and I think the cheapest kind of RepRap that you can make is right around like $350. It looks a little bit different than these. So it's kind of stemmed from another paper we wrote of the life cycle economic analysis of 3D printing. Basically what we did is we took 20 kind of at-home items. This is a custom orthotic. We have like a water bottle cage, shower head, phone cases, kind of different things you would use around the house, and we printed them out and we compared them to the high and low retail comparisons. So they're all printed on our RepRaps. They all range from cheap stuff from like shower rings all the way up to these orthotics, which can cost hundreds of dollars for just one. So it got a lot of press, which was great because it kind of exposed everyone to this idea of cheaper manufacturing with 3D printing. So it's kind of something to be able to springboard us onto this new project. So the premise of it was we could print whatever we wanted in the house without having any CAD design or any other that type of experience. So we have this graph of the number of designs on Thingiverse. Thingiverse is a repository of files, 3D files that you can just download and print out for free. So in March 28th of this year, there are right around 100,000 designs, and now there's over 170,000 designs. So you can see the growth of this Thingiverse is just exploding. Where I think when we wrote the paper, we had 0.02% of the designs on Thingiverse that we use. So that's what those 20 designs comprise. So some of our other data is we also wanted to take into account the energy used. The printers run at about 105 watts, so it's just kind of like one of your incandescent floodlights running. So they don't actually use that much power. And we also wanted to make sure that we were kind of printing out, an even distribution of if we have, 40 kilowatt hours or so, our mass is, linear, so that we can extrapolate it if needed. And then here is also our printing time versus energy use, so we kind of have like an even rate of deposition for our printers. Basically, so everything's uniform, our data is consistent, and then we can also extrapolate it out if we want to, make some huge claims. And we have some pretty high correlation there. So there is a list of all the different things that we printed out. The third one down, the iPhone 5 case, was actually customized. Thingiverse has a thing called a customizer where you can actually go in and change parameters and make designs different based on just what you want. So you can make something unique to yourself even without, CAD experience or anything. So what we found is everything costs $18.11 to print, which is, under $1 a part. And if you take the, low and high retail costs, which is we just use like Google Shopping, it would cost about $374 to almost $2,100 to buy. So you can kind of see your savings that you would have. And with printing, you don't have any shipping to pay for, you don't have any tax to pay for, and realistically, you don't have to wait very long because the printing time, I think for all the stuff, the longest one was the orthotic at just a couple hours. So within a couple hours, you can have something ready to go and usable. So let me kind of get into our project with the racking for the RVs. Currently, if you want to just put one panel on top of an RV, it costs $74 in just the racking. Now, to put that in comparison, your 200 watt panel could cost, it'd be about $150, give or take. So you're almost paying 50% off the panel just to stick it on your RV. So that's John, one of the co-authors that helped us with the work. And so this is our cost analysis. Here's the design that I showed. This is the little Z connector. It does the exact same thing as the aluminum one. And here's our standoff, which can be customized to a taller height, or you can add sections if you want to optimize your system. And we decided to use some reinforced steel bolts just to make sure it's strong. It may be a little too much, but better safe than sorry. And so we see a 84% savings in cost because per panel, this costs $11.64. Aluminum costs $74. Right, and then the other kind of advantage to it is since it's all customizable and you can just kind of input where you are, you can optimize your system for no money essentially. Since this part of it is only 56 cents, you can carry a bunch of them around. And as you can see here, we kind of have some kind of just standing on the face of the earth. And based on the time of the season, the sun is down here for your winter months and up here for the summer. So you can see that there's looks like it's 27 degree change, or 47 degrees, sorry, degree change of where the sun is. And the best performance of your solar panel will be when it's perpendicular to the sun. So if you're able to change your tilt angle, you can get greater than 20% or 20% more energy than just a flat panel. So we kind of took this idea of modeling it with our RV components because they were relatively cheap. $74 a panel isn't too bad. And kind of looking at where we're going to go next. So looking into ground-mounted solar panels. Right now it's $675 per kilowatt. That's 4 panels. So you take a $150 or so panel, and you take 4 of them, and it's going to cost you $675 just to mount them on the ground. And an interesting thing about that is that $675 based on the supplier that we already bought some stuff from. That's $675 if you have 1, 2, 3, or 4 panels. It doesn't change. I mean, it'll change if you get larger kind of larger systems, but if you only need one panel for a water pump or a light bulb or something, your costs are going to be dramatically higher. So kind of the next idea is, you can put them on apartment complexes, or just kind of on a balcony somewhere. Use that space, and you can't even really buy stuff that allows you to do that right now. That's just not out there. And then of course, bringing it to developing areas where instead of getting thousands of dollars, you can reduce that by 80% or so for the racking. And it makes it a little more viable for impoverished areas to be able to have a light bulb in their house, or you can even have one panel give 4 or 5 houses a light bulb. And then you can also go further, and there's been proof of concepts of solar powered RepRaps. So now you can even take the printer to the place that you want to go, and kind of print them out their racking on site right there. If you can teach them how to how to use it and everything, and they can print out new racking for new panels, and kind of build off of that. So this kind of brings up the question of the new supply chain, in a sense, is where you've already got your solar panels, which can power a laptop. You need a very basic one to drive a printer, so you can power your laptop, and you can this is kind of our development board here, which is what the printers run off of. So we can power all this stuff, the printer, and we're currently working on and developing our RecycleBot, which takes waste, plastic, milk jugs, pop bottles, anything that you don't want, melts it down into new filament to be used in your printer to print your panel racking. So you can drive the cost down by using waste, and then you can also drive the cost down by just using power that you're generating, and then you can also make it portable and bring it wherever you need to. So thanks for your attention. If you have any questions, I'd be happy to take them, or you can send me an email or check out our website if you want.
Very interesting. In your cost analysis, did you factor in the performance over the life? I mean, your costs seem to be the upfront purchase costs or the cost of manufacture. But especially when you compare like aluminum, which is a very high strength material, with plastic parts, which I assume is not as strong, you might have some failures over the life of your parts, and whether that's factored in sort of as a life cycle sense for the cost.
It could be. We kind of compensated for that in our design. We've made our part a bit more reinforced, a bit thicker, so that essentially it has the same strength as the skinny aluminum part, but we weren't able to do like a complete 20-year longevity study of it, which is what we're focusing more on that now with some of our projects on permanent like random stuff, to make sure that ours can last that long, so you don't have to print out new stuff all the time. Yes.
So I was interested in how you could take recycled materials and use that as feedstock. What's the typical feedstock for use in 3D printers? And what happens to the product at the end of its at the end of its day? Can it be recycled so you can run the stuff back through a printer and make new stuff with it, so it's kind of a closed loop, or does it wind up as some sort of waste product in itself?
So the two most common materials are ABS plastic, which is what Legos are made out of, and then there's PLA, polylactic acid, and it's a plant-based material. So it's a plant-based biodegradable material. So in theory, you can break down your prints. Right now with the RecycleBot, we cut up like milk jugs and then shred them to get them kind of a fine particle size to melt back down. The issue with a a finished print is that it can, depending on your fill percentage, if it's a completely full part, is like a heavy brick of plastic. So breaking that down might be a little bit more challenging, but there's no reason why you wouldn't be able to put it back in.